Okay, thank you. It's nice to actually be here. I last spoke at this conference in 2020 from my office in Ithaca. Actually, I was just telling Alvaro a moment ago, it's a little bit embarrassing in that the theorem that I gave a proof of then, it turned out like we simplified it dramatically after that. So I'm hoping something similar happens here and that some embarrassing video gets posted on YouTube, but at least there's some mathematics that comes out of it. All right, so let me start off. Oh, maybe 0. Everything is joint with Farshid Hajir and Christian Bear. Okay, so just quickly I'll sort of say a few things about pro-P groups because that's going to be the main object of study. These are inverse limits of P groups. And the standard example are the p-adic integers equaling the inverse limit of z mod p to the n. They have presentations sometimes, or at least finite presentations sometimes. So I'm just going to give an example. Now, we're not geometric group theorists, or hopefully we're not. Some of my best friends are geometric group theorists. So this is not Z cross Z for us, right? This is cross Z, but we need the pro-P completion. And then we get ZP cross ZP. Okay, so we'll be talking about presentations. They're going to play a little bit of a role in what we're doing. And pretty much any pro-P group, P finitely generated. And again, for a geometric group theorist, this would mean it's a finite set of generators. For us, it's a topological set of generators. We'll sort of be saying these finite elements, their closure generates the group. Generated. We'll have star. And this is the free pro-P group on D generators. I'm not going to define this. It would just sort of take us too far afield. But you can have a sense of what it is. So if you have a sense of what a free group on D generators is, it's sort of the same kind of universal object for a free pro-P group on D generators. And then there's a set of relations that you quotient out by to get your group G. Okay? And let me just state a theorem, well, with many parts. So if we have a free pro-P group with D generators, that's the first statement. The number of generators is just this H1. You could ask, what is the action of G on FP? It's a pro-P group acting on a P group. There has to be a non-trivial fixed point, so the action must be trivial. Oh, and this, maybe I should say, this also equals since the action is trivial. Okay, so this is true. It's the Hams from G to Fp, but I've left this big space because since this is an abelian group, we can mod out by the commutators. We can also mod out by the pth powers because we're going to a group that's killed by p. And we should probably take the closure, and it ends up being the same as this thing. A minimal number of relations is the dimension of this H2 with a trivial action. And these are sort of almost definitional. Now we're getting into something a little bit more interesting. We'll just give this the name R. The minimal number of relations. If G is finite, then let's see. This is a real theorem that takes some effort to prove. It's not super hard. If you look, for instance, in Koch's book on Pro-P-Galois theory, it's like, there's like in the middle of the book, there's maybe 15 or 20 pages where it covers everything involved, including what I'm about to say with step 4. This is generally attributed to Golod and Shafarevich. They actually proved it with d-1 squared over 4, and Geschütz and Winberg quickly got it to d squared over 4. And then, so before I write down 4, I'm going to say, without making any definitions, a group like this has a filtration. It's called, I think there's more than one, but the Zassenhaus filtration. So there's a normal subgroup, and inside that a normal subgroup, and so on. So it's reasonable to talk about the depth of an element, how far down in the filtration it is. Okay? So these relations are at some depth in the filtration. Now, what the next, oh, I should make a quick remark. This happens okay, let's see. I know I wrote this down wrong in my notes earlier today. Has no root in 0, 1. I think earlier I wrote that it had a root, but that's the opposite thing. Yeah. Oh, this keeps slipping down. Clip it to the t-shirt. Okay, cool. People can still hear me? Yeah. Excellent. All right. So if G is finite, this happens. And I talked about these depth of relations. Actually, so this is due to Koch and Venkov. So R2 is the number of relations of depth 2. R3 is the number of depth 3, and so on. So what this theorem is basically saying is, you know what, I don't know the depths of the relations. They're at least depth 2. Let's just assume a worst case scenario. But there are sort of refinements of this that people have gotten a lot of mileage out of. Okay. Yeah, sure. Well, yeah, no, in the interval 0, 1 on R. Yeah, no real root. Wait, am I misunderstanding you? Because when I think of the interval 0, 1, I think of that as a subset of R. Yeah, but fine. Okay. Cool. Okay. Let's see. Okay, so what is the point of this theorem? I may want to study a situation like this. And people did want to study the situation. There was a question, does every number field eventually sit inside a bigger number field with class number 1? And then if that was the case, you could get some mileage out of it. And it turns out once this stuff was understood with group, which is purely group theoretic, it's trivial to show that this is false. Okay? And, well, okay. Like everything in math, it's trivial if you know the right stuff. I'm about to write something down which, well, one thing is not a big deal, which is D equals the dimension of the class group of K, it's P torsion over FP. That's the number of generators of this group is going to be this thing. That's sort of coming out of just basic class field theory, that unramified extensions correspond to the class group. What's a little bit more involved is that R is less than or equal to D plus this. So let's just think about this for a second. Say we're going to vary K among degree 3 cyclic extensions of Q. Okay? Then the unit rank is going to be constant. So the unit mod cubes is going to be constant. Maybe this number can vary. So we're saying the relations is kind of linear in the class group. But over here, we need the relations to be quadratic in the class group for the thing to be finite. So it might not be hard to get an example where the class group is large. This is not going to be quadratic in it because it's at most, in this case, D plus 2 actually in the case I'm talking about. So you'll get an infinite P Hilbert class field tower. So let me actually just give us an explicit example of that. Where's my eraser? What's this at? Okay. So let's let P be 1 mod 3. So Q zeta P is a Z mod P minus 1 extension of Q. P is 1 mod 3. There's a Z mod 3 extension of Q in there. So I'm going to have these fields, not K3. 3 is not 1 mod 3. K7, K13, K19. 2, 3. Oh, I skipped one. How could I skip 37? So these are the first 7 primes that are 1 mod 3, and it's a trivial exercise to show that there are extensions ramified at all of them. You know what? Let's just call this K all, which will be the composite of them. It's also trivial to show this Galois group is Z mod 3 to the 6th, because the whole Galois group is Z mod 3 to the 7th, because there's 7 Z mod 3 extensions. But this is also unramified everywhere. Because we absorbed all the ramification here. And the ramification index of every prime is 3, so it's all absorbed here, so this is unramified. This is sort of standard genus theory. And if you've seen this stuff before, you've probably seen it with quadratic fields. I'm doing it with cubic fields for a reason. So maybe I'll give this a new name, L. And I can't really make that your responsibility, can I? Okay. M. This is the maximal unramified 3 extension of M. And what we know is D is 6, and R is less than or equal to 8. The reason R is less than or equal to 8 is the unit rank of a Z mod 3 extension is R1 plus R2, well, of any extension is R1 plus R2 minus 1. And in this case, R1 is 3. It's a totally real thing. And you subtract 1, you get 2. You don't have to worry about cube roots of unity being in there and messing things up by a little bit because it's totally real. And then you just sort of go back to high school and realize the quadratic 1 minus 6t plus 8t squared has a root. So this group is infinite. Okay, let's do the first thing here. I don't know about you, but I love playing with Desmos. Yeah, there, it's got a root, right? We can see the root. Oh. There's a question. Are there prime ideals here that split completely in this extension? I would guess the answer is no. Nobody actually knows the answer to this question. It's really hard. But it was asked, a question like this was asked by Ihara in 1983, how many primes decompose in an unramified infinite extension of a global field? Let's see. Oh, that's not what I want. What happened? Wait, what's going on here? Oh, it's black. Okay. I don't know why it turned colors. Okay, shouldn't matter. And you will see the paper highlighted in green, how many primes decompose completely in an infinite unramified Galois extension of global fields. He literally gave that the title of the question, yeah. Pardon me? No, that's a typo. I think it's responsible, either Hajir or Meir is responsible for that. Okay, that's Farshid's responsibility. Anyways, like he literally asked the question, and this actually is an interesting lesson, especially to young people. This problem had been around for 30 plus years. It turns out it's completely trivial to answer if you think about it the right way. Namely, in this extension, I said there was a filtration on this Galois group. That means that when you look at the fixed fields of the filtration, you're going to have an ascending tower of fields. Now, Chabotaro, and these are all finite over the base. Chabotarov's theorem will say that there are primes that split completely in here, and in any finite level. So what we'll do is we'll start at M100. And what we'll do is we'll choose Q1, splitting completely. Well, maybe we'll call it Q100. Splitting completely in M100, Q101, splitting completely in M101, Q102 in M102, and so on. And now what we're going to do is we're going to take this group and we're just going to impose relations, namely Frobenius at Q100, Frobenius at Q101. We're going to just mod out by the normal closures of these Frobenius elements. And what we're doing is we're introducing a relation of depth 100, depth 101, depth 102, and so on. So mod out by all these Frobenius elements. And what you're going to get is that as the polynomial. And if that has a root in 0, 1, the group is infinite. So let's go back to Desmos. I mean, it's sort of obvious it has, wrong thing. Sort of obvious it has a root, but let's put that in. Plus x to the 100th. Sorry. 100. I'm summing the geometric series there. Yeah? Yeah. Yeah, yeah, there's a root. 2 roots, anyways. So this group is infinite. Yeah.
Does Q100 lie over Q101?
No, you first choose Q100, then you choose a different prime that's in the 101st filtration, and so on. And you do that, and what this says is that somewhere up here we've put this new thing that is now all the Frobenius elements lie up in this little bit. So all the primes from Q100 on split completely up to this bit. So the answer to Ihara's question is infinitely many can split completely. You can't have a positive density in an infinite extension. That's not going to happen. So you can get a countable number, and that's all you can get. But it really wasn't very hard, right? It was just, and hence the word cutting. The modding out there. We're cutting by various things, and we get an answer to Ihara's question. So the moral is, again, like, maybe just because a question hasn't been answered for 30 years, it's because no one thought about it the right way. All right, let's mute that. How are we doing for time? 25. Okay. Yeah, was there a question? No? Of this particular thing? Almost nothing. The only place it had anything to do with was with 6 and 8. And so that it was a cubic extension meant that the difference was 2. And the 6 was sort of more clear. So that's really all that it had to do. I mean, you can do it, if you want to do, it would be more standard to do it with quadratic, a multi-quadratic field and do this. And it's if I had put in 10 more primes, the amount of room I would have had to cut would have been great. And I might not have had to start at the 100th level. I could have started maybe at the 10th level or something like that. Okay.
Ravi, maybe you should just say that 1 minus dt plus rt squared, you can't just kiss the x-axis and go up. It has to actually go below.
I thought if it kisses, it's still infinite.
It's still infinite. But then
Oh, right, yes. Yeah. So what Farshid is saying is, if you just touch, if you're tangent to the x-axis at this level, you can't cut anymore. Because the moment you start adding in more relations, you push yourself above. So to do cutting, you actually have to be below. But the group is actually still infinite if you just touch the x-axis. But yeah, this is a problem because we ran into examples where it just touched and then we weren't able to cut, unfortunately. Okay, cool. Any other questions? All right. So why did I use a Z mod 3 extension as opposed to a multi-quadratic thing, which is standard? And I don't think you'd ever run into this in any book. Well, this is exactly what the OpenAI proof used for the new lower bound for the unit distance conjecture. It decided to work with the Z mod 3 extensions, and then it wanted one where the tower was infinite, but it also needed primes that split completely. And the point being that if it's not, the proof is easy, but again, it might not have been completely obvious that because it didn't happen a year after Ihara published his paper, even though all of the tools that were needed existed. Okay. Maybe I'll talk about one more example before sort of briefly talking about the unit distance conjecture. That's not my area of expertise, but I will talk a little bit about it. Let's see. So this is what's called the root discriminant. You take the discriminant of a number field and you raise it to 1 over the degree. And in some ways, this is a better metric, and if you're familiar with it, not as a number, but as an ideal, it's essentially the different. Okay? And if you remember, if you've studied difference, you may remember that, oh, they're multiplicative in towers in a nicer way than discriminants are. So this is one thing that's nice about them. And a fact that's not hard to prove, I won't prove it, is that root discriminants are constant in unramified towers, in unramified extensions. Extensions. And 2, they're bounded in tamely ramified pro-P extensions. Maybe I should say something that I think is a good example before I This is a good exercise. Just compute the discriminant of the p to the rth cyclotomic field, figure out the root discriminant, and you will notice that goes to infinity as r goes to infinity. So the point being that if you want bounded root discriminants or unramified towers or something like this, you have to stay away from cyclotomic fields or p-adic cyclotomic fields. And that means you kind of have to stay away from algebraic geometry. Right? Because most of the Galois, at least the ones that I run into, p-adic Galois representations coming from algebraic geometry almost always contain, or maybe always contain, the ZP cyclotomic extension. So algebraic geometry is usually the right answer for everything, but not for, well, maybe I should rephrase. The right tool, it doesn't mean you can answer the question with it necessarily, but not for these sorts of things. So, like, because of this, these are the wrong kinds of fields to study. Yeah?
For number 2, you want to say the number of primes.
Oh, yeah, no, yeah. I thought that. I mean, okay, fine. Extensions with finite number of ramified primes. You can certainly have infinitely many ramified tame primes. I was like, as I was writing it, I was thinking, I have to put that down. Okay. So you can get infinite towers of number fields with bounded root discriminant, including the one I just erased. As long as you have an infinite unramified tower, you're constant on the root discriminant all the way up. So there exist infinite towers of number fields with bounded root discriminant. Root discriminant. Okay. Odlisco has some bounds, and let's see. So we're going to talk about for some kind of infinite tower. It's a little more complicated for a finite number field. But if it's, let's see, totally complex, totally real, there are ways to deal with mixed signatures, but let's not worry about that right now. the root discriminants are 8 pi, always bigger than or equal to 8 pi e to the gamma as you go up the tower. And gamma is Euler's constant, the 0.577 thing. And over here, it becomes 8 pi e to the gamma plus pi over 2, and that's roughly 215.33. So I don't know why this thing is in black, but that's okay. Here are sort of the records up top there. So in 1978, Martinet got infinite towers where the root discriminant in the totally complex case was 92.368, and in the totally real case, 1,058, which are both fairly far away from these numbers. Hajir and Mer improved these numbers to 82.1004 and 954, 24 years later. Another 4 years later, my former PhD student, Jason Martin, got the totally real case down a little bit. This is about some brute force looking through fields and then being very clever when you find fields and sort of having to be smart about what you do with them. And then Hajir, Mer, and I got the far column where we improved these. Now, there are these numbers, the 0.7244 and so on. And what those are is sort of this. Let's see if I can do this. Orange. Really, that's the right thing to study. You want to take your root discriminant and then divide it by the Odlyzko bound, this in the totally complex case, this in the totally real case, and take the logarithm. So that sort of measures how far you are away. Yeah, this screen isn't going to work. From where you want to be. So Martinet was 0.7244 away and 1.592 away, and the new records are improved a little bit, reasonably well, to 0.5608 and 1.382. If you actually look at it, the totally complex case, we really haven't made as much progress as we would like in getting to these bounds, if we believe them. I'm not sure whether I believe there exist towers of number fields with these root discriminants this small. Certainly, a lot of people have looked for a long time and not been able to find anything. So let me just, yeah, okay. I'm not going to get into the details. I'm just going to say that if in 2018 or 20, when these new records were found, the three of us could have gone back and had a 1-minute conversation with Hajir and Mer in 2001, I think they would have just immediately gotten what they needed. It was like this business of cutting, where we realized we could take their examples and just sort of mod out by something and then get substantially better results. So that is where I'm going to stop talking about the arithmetic of cutting, I think. And switch gears. And say that, just recall what the unit distance conjecture is. And how towers of number fields played a little bit of a role. Okay. Problem, maybe. Since now the conjecture has been disproved. And the problem is, given n points in the plane, how many pairs can have exact distance 1 between them? And okay, you make your nice rectangular grid, and it's pretty easy to see that there's a reasonable lower bound. I actually have not studied the upper bounds, but let's see, it was big O of n to the 1.5, and then that got improved sometime later to big O of n to the 4/3, and I think that's where we still are for the upper bound. And Erdős had conjectured a lower bound of big O of n to the, I think it was 1 plus 1 over log n, something like that. But the OpenAI proof and the delta is pretty small. I mean, it's very strange to say. In the original proof, the delta is pretty small, but the new proofs have it to like 1.013 or something when the whole thing's 3 weeks old. I'm not used to proofs evolving quite that quickly. So where do towers of number fields come in? That's kind of what I wanted to convey a little bit of, and how they play a role. And where does splitting come in? Yeah. Those we looked around, and those are answered, right? Once you get to n bigger than 3? Bigger than 2.
4 or higher, it's been low for a while. And I think n equals 3 also.
Yeah. What exact bounds on either side? It's completely solved. I mean, I don't know about constants, but yeah. I don't remember what the bounds are, but we just sort of, spent a few minutes Googling around to see, wait, could towers be helpful there? And the answer is no. I mean, maybe you could prove those bounds again, but so well, one way they enter is the root discriminants say the same. And discriminants are about lattices. And you're going to have a lattice in a higher dimensional space. And the volume of the lattices won't be changing as you go up the tower. So you'll have a series of lattices, and their covolumes, really, or volumes, whatever you want to call it, won't be changing. And that's an important thing. If as you have a tower, everything's changing and growing, then it's going to be hard to control things when you're trying to build these points. Now, lattices, of course, are lots of points, but they're in higher dimensional spaces. So you need to project down to one copy of C, right? We're going to have some totally complex fields. We're going to have the exact same L we used before with those 7 cyclic extensions. And we're going to have L infinity of 3. And then we're going to join I. L empty set of 3, not infinity. And this is totally complex, but it's a CM field. And one interesting thing about this is that if alpha is in here, and the absolute value of alpha, the size of alpha equals 1, now what does that even mean? There are multiple embeddings into C. But if it equals 1 in one embedding into C, it equals 1 in all embeddings. That actually is a homework problem. It's not hard. In one embedding into C implies for all embeddings. Okay. So what you might want to do is if you have some big lattice in some ring of integers, I don't know, how about R of I? Oh, R, that's not good. Looks like C. It's called D. If you have some lattice inside here, what you might want to do is intersect it with a ball of radius r minus 1. And then you might want to hope have lots of elements of size 1 in the lattice and call that set U. And then if you do U plus BR minus 1 of lambda, so that's the intersection with a ball of radius r minus 1 with your lattice. Now, this will be contained in a ball of radius r, because these things all have size 1, so you're not moving by much. Ultimately, what we're going to do is project down to one coordinate, and the projection will be injective. But I don't think that's really the central point for this argument. So we're going to have this, and what we would hope is that this is big. This, we kind of know what it is. You know what the volume of a ball of radius r minus 1 is, and you divide by the volume of the lattice. So you'll be able to figure out how many lattice points there are in here. But of course, you know, if you take all the points in here and all the points in here and do the translations, the product is how many are a unit distance apart. Right? The whole point of having lots of things of size 1 is it gets you unit distances. Okay, so this would gives lots of unit distance pairs. So that's one way. Well, I haven't even remotely answered the question yet. I've just talked about lattices. Where do the unramified towers enter? Well, how do you get elements of norm 1 in a field extension? What we really understand in here are prime ideals. So what we'll do is we'll sort of take a bunch of prime ideals and maybe sort of take some products of them, but there's only so many ways that the products can appear in the class group, because the class group bounds the number of non-principal ideals. So what we want to do is sort of create some system of prime ideals here where there's going to be lots of products, and then we'll take quotients of these products, and many of them will have to be principal, because there'll be more products than the class group. And how are we going to do that? Well, if you have a prime that splits completely, you've got lots of ideals. Okay? So what we want, let's see, how am I doing? Okay, I'm running out of time. Primes to split completely. This will give lots of prime ideals. We'll take the products of these primes, qi to some powers, bounded, and this gives lots of ideal classes. Many will lie in the same ideal class. We'll take quotients to get principal ideals and elements. Principal ideals alpha. And then we will, because we're in a CM field, we'll divide alpha by its complex conjugate, but we'll apply complex conjugation. And that will be something that has norm 1. And that's sort of the crucial idea, in that you get these things of norm 1 and you can make everything work. You could reasonably ask, why can't I do this in one field? Just, pick some big field and work from there. And it turns out the way this works is this thing, this U, if you sort of bound your denominators, and that's what's going on with these quotients. These powers are bounded, so the denominators are bounded when we do our division. If you bound your denominators, this set will be finite. And even if you increase the size of the balls, that's not going to help. So you sort of need to go up higher and higher fields to make this work. So I think there were many sort of novel ideas. I think using an unramified extension had been done before, but sort of using a tower of unramified extensions to sort of work on this particular problem had not. And I'm way over, so I will stop.